We are doing Chapter 9, Section number 5, Ratio Test, Root Test, Comparison, and also Limit Comparison Test. So the ratio test, let me show you this. We will be looking at a series a sub k. So you are going to have to find a sub k plus 1. So basically in your series, you replace all your k's with k plus 1, and that gets you your a sub k plus 1. And you just find this limit. And when you find it, you find what's called r. Now, if r is anything between 0 and 1, including 0, then the series converges. If it's bigger than 1, then the series diverges. And if it equals 1, then you don't know. The test hasn't given you any information, and you have to find another test. So that one, sometimes it doesn't work. So this is not a test that will always work. There's certain conditions. You'll kind of get a picture when it will or will not work. And I will do 3 examples and show you. And so, kind of a hint, when you have factorials, it often works. And when you have something to a power, a kth power, it often works. So let's go ahead and do this. Number A, or letter A, we need to find, well, a sub k is just 10 to the k over k factorial. So a sub k plus 1, you replace all the k's with k plus 1. Now you find the ratio and take the limit. So we're going to take the limit as k goes to infinity, and we put the k plus 1 term on top, and we divide it by the original. Now when you do that, it's equivalent to multiplying by the reciprocal. So we will rewrite this and then start to cancel. So we take our original and multiply that by the reciprocal. So here we have 10 to the k, so we have k tens. On top, if you look, you have one more on top than you do on the bottom. Because on the bottom you have k, on the top you have k plus 1. So when you cancel those, you'll have 1 left on top. And that's what we have here. Now the factorials, let me just do a little side note for you and show you how this works. If I have 5 factorial over 4 factorial, remember what that means. That means 1 times 2 times 3 times 4 times 5. And at the bottom, 1 times 2 times 3 times 4. And then all these numbers cancel except a 5 on top. So that's kind of what's happening. Now, let me show you a little side work on what we have here. We have k factorial over k plus 1 factorial. So k factorial over k plus 1 factorial. K is all the numbers all the way up to k. K plus 1 also has all the numbers up to k, but then it goes one further to k plus 1. So everything up to the k's cancel, leaving a k plus 1 on the bottom. So when that factors, I'm left with on the bottom just k plus 1. So now on the next line, on top I have a 10 left over, on the bottom a k plus 1, but that equals 0. And if you look, that means it's convergent because if the number is equal to 0 or less than 1, it is convergent. So our conclusion, therefore, the series 10 to the k over k factorial converges. Now, a couple of the comments, we could have used the divergence test. Now, if we would have taken the limit of these terms, you would have found that that is terms approach 0. So the divergence test would have shown that you don't know. It wouldn't have helped you. As far as the integral test, that you would, good luck on integrating that. And so some of the other tests we had would not work on there. And so there's kind of a progression on what things work and don't work. And you have to have a feel for what does or doesn't. All right, so we are going to continue. We're going to do another one. Let me see. Let me erase this all, and we'll do part B. So B, your a sub k, we're doing part B, is just k to the k over k factorial. And a sub k plus 1 is k plus 1 to the k plus 1 over k plus 1 factorial. And then your r will be the limit as k goes to infinity. So the good thing about this one is pretty easy to set up. The algebra, sometimes usually it's pretty easy. The only problem is it's limited, what we divide by, sorry. It's limited into when it will work and when it won't. Now for this, I can rewrite it. So I multiply by the reciprocal. So it's a pretty similar process each time. All right, and now the canceling, just like the last one, this cancels with this, and on the bottom we have an extra k plus 1 term. Now this is where it gets tricky. That and that, can you cancel them? And the answer is going to be not really. So we'll have to talk about this. Let me go ahead and, okay. Yeah, this works out nicely here. Something happens. So notice this is a k plus 1, that's k plus 1. So one of those are going to cancel. So you're going to lose that one because just one cancels. So I'll go ahead and do that in red. That k plus 1 cancels that one there. Let me show you what we have left. We have k plus 1 to the kth power over k to the k power. Whoopsies. I don't even need those parentheses. And so we have on top something to the k power, on the bottom something to the k power, and we can combine those because they're both to the k power. So we can rewrite this as limit as k goes to infinity, and then we have k plus 1 over k, it's all to the kth power. Now if you look at that, I'll let you pause a little bit. What do you see there? Okay, this is where we're going to have to do some side work again. So inside is going to be 1, and that's going to be infinity. That's actually going to be a L'Hopital's. That is a L'Hopital's. So let me do side work. I need some space, so I'm going to move this out of the way for now. And on the side, limit k goes to infinity. Let me back up there. K plus 1 over k to the k. Again, what's happening? This approaches 1. That approaches infinity. So I can rewrite this. And in fact, let me get rid of this limit real quick. And let y equal this. So now we ln both sides. And if I ln, I can use the p in front of the log rule, so that k will come out in front. So I'll get k ln of k plus 1 over k. Now we're going to look at the right side. We're going to find the limit of the right side. So the limit as k goes to infinity of k ln of k plus 1 over k. Now look what's happening. This still approaches 1, but when you take the ln of 1 is 0, so that all approaches 0. That's infinity. Now that is not of the form of L'Hopital's yet. L'Hopital's is either 0 or 0 or infinity over infinity. So we're going to move the k to the bottom using algebra. So the top will stay the same. The bottom becomes 1 over k, and to convince yourself, if you multiply by the reciprocal, that'd be k over 1, and then that would be that. So now we have a L'Hopital's because the top, that approaches 1, ln of 1 is 0, and 1 over infinity is 0. So now we do definitely have a L'Hopital's. I need so much more room. I'm going to continue right here. So since it is L'Hopital's, I take the derivative of the top and the bottom. So on top, it's ln of box. The derivative of ln of box is 1 over box times the derivative of box. But the derivative of box is going to be low d high minus high d low over low squared. So low d high minus high d low all over low squared. And so that's the derivative of the top. The derivative of the bottom, that's k to the negative 1, right? K to the negative 1, so it's negative 1 times k to the negative 2. Now let me rewrite all of this. So this, I'm dividing by that. Let me double check. I just lost my train of thought. So the derivative of the top is ln of box. So it's 1 over box. Why is that not writing for me? I'm not sure what. Oh, I know what happened. I got the wrong tool. Something just is freaking out here. Okay, there we go. I don't know what happened. So the derivative of ln box is 1 over box times the derivative of box. Okay, so that is correct. I'm going to multiply. This is in the denominator right here. We're dividing by that. So I multiply by the reciprocal of that. So this would be k over k plus 1. And then on top, let's simplify the top here. That's k, and distribute the minus sign. So it's minus k minus 1. Those k's cancel. So on top, we're left with negative 1. And then on the bottom, we still have k squared. But, oh no, let me keep going. Now this is negative 1 over k squared. So I multiply by the reciprocal of that. So the reciprocal of that is k squared over 1, and that's negative. And we're taking the limit as k goes to infinity still. So limit as k goes to infinity. Let's simplify these things. K squared and k squared cancel. Negative and negative is positive. So we're just left with k over k plus 1, which is 1. Wow. So what equals 1? It's actually this limit equals 1. The limit of the right side equals 1. Okay? So back to this. This equals 1. ln of y equals 1. How do you get rid of ln? You have to e both sides. Don't you love L'Hopital's? Y equals e. So the limit of all that, we get e. Craziness, huh? So let's go back. This equals e. Is e between 0 and 1? No, because e is 2.7 something. Since r is greater than 1, I would say since e is greater than 1, therefore the series is divergent. The original series, k to the k over k factorial, is divergent. Okay? So that's going to be the second one. We have one more to go. And let me erase all of this. That was a lot of work. A lot of work. Okay, part C. Let's do it. Okay, our a sub k would be e to the minus k times k squared plus 4. So our a sub k plus 1, replace all the k's with k plus 1. Whoopsies. There we go. And so r will be the limit as k goes to infinity of this one all over this one. And now we have some simplifying to do. So the negative exponents are going to cause these to switch places. So let me go ahead and do that. The limit as k goes to infinity, it's going to switch and become positive. And then on the top, I'm just going to multiply that out. K squared plus 2k plus 1 plus 4. So I just squared this binomial. And on the bottom we have this. Now, these, I have k of them on top. I have k plus 1 on the bottom. There's one extra e on the bottom. So when I cancel those out, I have an e left over. All of this will be the limit as k goes to infinity. On top, k squared plus 2k plus 5. On the bottom, ek squared plus 4e. All I did is I distributed the e to both of those. So this limit, if you remember from last year, you should divide top and bottom by k squared and take the limit. If you do that, your limit will be 1 over e. So 1 over e is less than 1. Therefore, this series converges. Now, we didn't have one that was inconclusive. We'll probably want to do one of those, so let's do a situation where this test doesn't work, and you'll see. So one last example. The harmonic series, we know this diverges. And you wouldn't have to test this because you know there's a theorem that says this diverges. It's automatic. But if you wanted to verify using the ratio test, let's see what would happen. Our a sub k is 1 over k. Our a sub k plus 1 is 1 over k plus 1. So our r will be the limit as k goes to infinity of 1 over k plus 1 over 1 over k. Then we multiply by the reciprocal. So we have 1 over k plus 1 times the reciprocal, which is k over k plus 1, which is 1. But if it equals 1, the test is inconclusive. So therefore, this we don't know. The test did not help us. We are stuck. So that's how that works. All right, now we're going to do the next test. The root test. So in the root test, and this is very, okay, so this one, the p's and r's are similar. Here, if your p is between 0 and 1, including 0, it converges. Well, same thing. Here, if your p is if your p is greater than 1, it diverges. Here, same thing. You see the connection between the two. Here, if your p equals 1, it's inconclusive. You don't know. And the same thing here, inconclusive. So because of that, I think you should be able to remember these conditions. But what's going to confuse you are just the conditions when it converges, when it doesn't, because there's so many other tests and they have different numbers that work. It gets a little confusing, so you need a lot of practice. So this is an interesting one. It says if you take the kth root of your terms and take the limit, that gives you your p. Actually, it might be a rho. That's a Greek letter. I think it might be a rho. So when does this work? It works well when something's raised to the kth power. So when you take the kth root, it cancels out. So that's what's happening. So you see here, hey, I have a kth power. If I do the root test, I can get rid of that. So that's the thought process on that. So let's go ahead and do this. Want the limit, this is part A, as k goes to infinity of the kth root of your terms, and that's going to be 4k squared minus 3, 7k squared plus 6 to the kth power. And so the nice thing is the kth root and the kth power cancel, and it leaves me with this, just the inside. 4k squared minus 3 over 7k squared plus 6. Now from AB, you should be able to find this limit. Technically what you do is divide top and bottom by k squared. If you don't remember that, you might have to review that. But I know this answer is going to be 4/7. 4/7 is between 0 and 1. So I can say, therefore, this series converges. Done. So that's it for that one. Let me do another example for you. Let me erase this stuff. We'll now do B. So we have the limit as k goes to infinity. That's the kth root of the terms, 2 to the k, k to the 10th. All right, what do we get from this? The top is just going to be 2, because the kth root of the kth power cancel out. On the bottom, you're going to have k to the 10th, and the kth root is 1 over k power. And so you have 2 over k to the 10 over k power. All right, so we need to find this limit. Now this is going to be infinity, and that's going to be 0. Infinity to 0. How are we going to get that? That to me looks like it's going to be another L'Hopital's, so I want to do some side work. This will be good review for you. Not review, actually, I can't remember if I did this earlier this year. We will talk about it. But if not, you're going to learn this. Let y equal k to the 10 over k. So a reminder, in the limit, this is 0, and this is 1. 0 to the 1 power is a form of L'Hopital's. So I take the ln of both sides, and I will p in front of the log. So what I did, I brought the exponent in front of the log here. And now I'm going to take the limit of the right side, as k goes to infinity. This is going to be 0, and that's going to be infinity. Well, I can rewrite this. I'm going to move this part to the bottom using algebra. If I move to the bottom, it flips. You can double check that. Multiply by the reciprocal, so it'll become 10 over k, and that will be the same thing. So we verified that that is okay. Now let's continue moving on. So we have L'Hopital's. Since the top, ln of infinity is infinity, and infinity over 10 is infinity, we can do L'Hopital's. The derivative of the top is 1 over k, and the derivative of the bottom is 1/10, which I can rewrite, multiply by the reciprocal, so we have 10 over k, which approaches 0. So ln of y approaches 0. In the limit, this approaches 0, so ln of y is 0, i.e. both sides. Those cancel. Y equals e to the 0, which is 1. So this all equals 1. Now what do we say about 1? If it equals 1, the test is inconclusive. Oh, wait a second. I am a liar, pants on fire. Good thing I caught that. The bottom equals 1. The top, okay, let me erase this. The side work we did is just that. The bottom equals 1. The top is 2. So our R, or rho, equals 2. It's greater than 1. Therefore, it diverges. Therefore, our series diverges. Okay, there's our conclusion. Let's keep going. We have 2 more tests to do. All right, this is called the comparison test, and it should make sense to you. You don't have to memorize this one because it makes sense. Here's your order. B is the biggest, A is smaller than B, and they're all positive. Okay? So B is bigger than A sub k. If B sub k converges, so I've drawn here the partial sums of the series b sub k. And converging means it reaches a sum. So in this case, it converges to m. Now, if, let's look at this, a sub n or a sub k is smaller than b sub k or equal to, that forces, and I'll do it in red, put it there, that forces our red series to be underneath or equal to. Now, if it's underneath, can it cross and go above and be divergent? No. It is stuck underneath. So what we have is, it's comparing. If b sub k has a limit, then a sub k is underneath it, smaller. It can't go above. It's smaller. And so somebody say, what if it goes down? Well, it can't, because the terms must be all greater than 0. So that can't happen. So the conclusion is a sub k must also converge. That's what that's saying. Our second one is a slightly different situation here. Now we have the situation where b sub k is smaller than a sub k. So if you know you have something that diverges. Oh, let me go back to this one. What if a sub k is above? What if instead of a sub k being smaller, a sub k was bigger? And this is why you don't have to memorize. If a sub k was bigger, a sub k is on top here, right? Now, two things can happen. It could flatten out on its own and have its own convergent series, or it could go up higher. So that would be inconclusive. So if you have a known convergent series and something's smaller, it also has to converge. But if something's bigger, it could converge or diverge. It's inconclusive. So it's only when you have a convergent and another unknown smaller than that do you know anything. So here we're starting with a divergent series. B sub k diverges, keeps getting larger, no limit. Now, if I found something smaller, a sub k, so suppose a sub k is smaller, it could shoot up or it could flatten out. It's inconclusive. It doesn't help you. Okay? So in this case, only when a sub k is larger or equal, it's forced to go up because it has to stay above this. It cannot flatten out because a sub k is bigger than b sub k. So the conclusion is, if you have a divergent series and you have another series that's bigger than that, it has to also diverge. That is the comparison test. That's what's happening here. All right. So let's do this. How do we do this test? If you look at this, you have to compare that to something. What can you compare that to? So you need a known series that you can compare that to. What do you know that might look like that, that might be similar to that? Now, as k goes to infinity, that becomes more insignificant. And if you look at these, the 3 cancels the 4, leaving just, it looks like 1 over k to me. So because of that, I lean towards, hey, maybe I can compare it to a known series, 1 over k, 1 over 2k, something like that. And more likely, I would compare it to 1 over 2k. And here's why. And you might say, well, we don't know 1 over 2k. I will explain that to you. 1 over k definitely diverges. That is a harmonic series, right? Well, what if I multiply that by 1/2? If something goes to infinity, is half of infinity going to change it? No. So you can argue that 1 over 2k is convergent, divergent also. So we need to do a comparison test. So if, oh, I shouldn't have erased that. 1 over 2k is divergent. So that's our known divergent. That's a situation where we know something keeps getting bigger. We have to show our unknown is bigger than that. So here's our unknown. We need to show that k cubed over 2k to the 4th minus 1 is bigger than 1 over 2k. All right. Now k is always positive, so I can just multiply both sides by the common denominator. So I'm going to multiply both sides by 2k and 2k to the 4th minus 1. 2k to the 4th minus 1. Those cancel and those cancel, leaving me with 2k times k cubed is bigger than 2k to the 4th minus 1. Let me multiply that. I get 2k to the 4th and 2k to the 4th minus 1. Let me subtract 2k to the 4th from both sides. On the left side I get 0. On the right side I get negative 1. This is always true. Since it's always true, that means my original statement is always true. So now I have my conclusion. Since 1 over 2k diverges and k cubed over 2k to the 4th minus 1 is greater than 1 over 2k, therefore the series diverges. That's the comparison test. So what we did, we have a known divergent series that keeps getting bigger. We proved that we have an unknown that's bigger, therefore the unknown must also diverge. That is an example of comparison test. I need to erase all of this stuff here, so let me erase that. You can skip forward a bit if you wish until I get to B. So now we're going to do B. Let's keep going here, sorry. We have ln k over k cubed. Now what are you going to compare this to? So here's what you might think. The top thing, ln of k, that's that. Y equals k is bigger than that, right? So to be conservative, if the top were k, if it were k, these would cancel, leaving 1 over k squared, right? 1 over k squared is a p-series that converges because our p is bigger than 1. So my thought is let's compare it to 1 over k squared. So you would say 1 over k squared converges. It's a convergent p-series. So this is a situation where we have something we know converges. The only thing we can prove, if we have some unknown that's smaller, it also must converge. So what's smaller? We want to show that ln of k over k cubed is smaller than 1 over k squared. Can we do that? Let's multiply both sides by k cubed. Those will cancel, and we're left with 1k there. And we have ln of k ln of k is less than k. Is that true? How do you get rid of ln? You e both sides. Those cancel, and we end up with k is less than e to the k. Is that true? Is it? Yeah. This is exponential. This is linear. Exponential is definitely bigger. So that is true. So we have proved what we wanted to. We have shown we have a known convergent series, and we've proven an unknown smaller than our known. So our conclusion is, therefore, our unknown series also converges. All right, so that worked out nicely. Let's keep going to the last example. All right, we have the limit comparison test. And this is actually easier than the comparison test. It is easier. So let me go over this with you. What do we have here? We have two series, okay? And the bottom one, we know whether it converges or diverges. We know. And the top one, we don't know. And we take this limit and we get some L. So if this limit is anything other than 0 and infinity, bam. Whatever the bottom one does, the top one does. Okay? The 0 and infinity case, we're going to have to look at to understand what's going on there. So let me do a couple examples. I need another page here. I put it in the wrong place. It went in the wrong place. I want it below this page. Let's see if I can do that again. There we go. So limit comparison. So it's similar to the comparison test, because if you look, as k goes to infinity, we kind of ignore those. We look at that, and we get k to the fourth over k to the sixth. That's going to be 1 over k squared. So my clue is I probably want to compare it to 1 over k squared. So I take the limit as k goes to infinity, and then I have this function, my unknown one, and divided by my known, which we know that this series converges, right? We know that converges. So I'm going to multiply by the reciprocal. So when I multiply by the reciprocal, it's going to be times k squared over 1, right? And then I multiply this out. On top, we're going to have 5k to the 6th. I'm going to distribute this. Minus 2k to the 4th plus 3k squared. On the bottom, I get this. Now, to take this limit, we did this in Calc AB. You divide everything by k to the 6th. This limit will come out to be 5 over 2. And so that's pretty easy. If that's anything other than 0 or infinity, they both do the same thing. Okay? If L is anything between 0 and infinity, then both of these series do the same thing. And our L was definitely between 0 and infinity. Therefore, our unknown series, this long old big old thing, also converges. So that is the first example of limit comparison test. Now, similar conditions, they must all be positive terms, just like the comparison test. And let me do another example for you guys. All right. Part B. So what does this remind you of? So the top is similar to what we did before. Is it the same one as we did before? Ln k over k cubed? Basically, okay, so the top, ln k looks like that. Linear, that's just k. That's k, that's ln k. So to be conservative, we put a k there, and that reduces to 1 over k. So we're going to compare this to the harmonic series. 1 over k diverges. It's a divergent harmonic series. So that seems to be our candidate. We take the limit as k goes to infinity, and we have ln k over k squared, and we divide it by our known divergent, which becomes, multiplying by the reciprocal, times k over 1. So one of these will cancel out one of those. So we end up with ln k over k, but that's infinity over infinity. That's L'Hopital's. So by using L'Hopital's, the derivative of the top is 1 over k, the derivative of the bottom is 1. That's going to be 0. Okay, wow, what do we do with 0? Let me explain the situation. If L is 0 and B sub k converges, then A sub k converges. But we don't have that situation. Our B sub k diverges, so we're kind of stuck. We are inconclusive. We don't know. And how do you remember that? So here's where we use some logic. So case 2 here, if the limit as k goes to infinity of a sub k over b sub k equals 0, so if this equals 0, what does that imply? So let's think about this logically. If b sub k converges, right, and this goes to 0, the top one's got to be smaller. The growth rate of the top must be smaller than the bottom to go to 0. So if the bottom converges and the top has a slower growth rate causing 0, the top also must converge. That's what it's saying. But if the bottom diverges and it equals 0, you know the top has a slower growth rate. It's a slower rate, but it doesn't mean that it diverges. It could converge or diverge. That's why it's inconclusive. So that's what's going on with case B2. And that's what we had here. We had the bottom is divergent, right? 1 over k is divergent, so the bottom's divergent, and it equals 0. If the bottom's divergent and equals 0, the top has a slower growth rate, but it doesn't tell you anything. It could converge or diverge because it's smaller than a divergent. It's smaller than a divergent, but you don't know if it flattens or continues to diverge also. So case number 3, and again, you shouldn't have to memorize this if you understand the logic. We have the limit as k goes to infinity of a over k over b over k, and that's infinity. What do you do when you get infinity? Well, I didn't mean to do that. If you get infinity, well, if this diverges, okay, say it's divergent, and it goes to infinity, well, to go to infinity, the top has to be a larger growth rate. It's a bigger growth rate to go to infinity. So it has to grow faster. Well, if the bottom diverges and the top grows faster, it has to go even bigger. Therefore, it must also diverge. All right? But if the bottom one converges, and it goes to infinity, the top has a bigger growth rate. Well, I don't know what it does. It might flatten, it might not. So it's inconclusive. So that's the second two cases. You don't have to memorize that. That's just logical thinking. All right? That is the limit comparison test, and that is the end of this long video. Bye-bye.